All right, so let's see here. So we want to see the registration process. The easiest way to create multicast traffic is simply to do a multicast ping. And actually this will be easy. The reason I was hesitating is because, for example, if I did a multicast ping from router 4, when you initiate a multicast ping from a router, he will actually send out that multicast packet, that multicast ICMP packet, on every single interface he has that has PIM enabled. I mean, he doesn't even bother to check mRoute state or anything. He just copies it and sends it out every single packet. And I didn't want that. But in this case, I don't have to worry about it because on router 5, he only has one interface anyway. So let's see here. We want to capture the... So this is going to be the multicast packet. It's going to come down this way. And we want to see that multicast packet as it's encapsulated in a PIM register. And then we also want to see, as soon as the RP gets that, we want to see him send a PIM S, G join to open up his shortest path. Then we'll see the actual multicast itself flowing down in its native form. And then lastly, we want to see the RP, once he gets that, sending a PIM register stop, because that's going to be the process. So in order to do that, let's see here. Why don't I just capture everything going in and out of router 3's fast Ethernet 00. So router 3, his fast Ethernet 00 is port 0/5 on the switch. All right, yep, 0/5. Okay, so we should be ready. So let me go now to the source. And I think it's 999 is what I'm using. And I'll repeat that 100 times just to keep it going for a while. And let's start the sniffer trace. Okay, there we go. That was enough. Okay, so here is the register. So we don't actually see the, because I'm only capturing on, let's go back to this. Because I'm only capturing on data coming in and out of 00, we didn't actually see the native multicast as it came into router 4. But we do see the register message. So here it is, PIM register. So this is the IP address 4545. Let's just check here. Router 4 should be doing the registering, not router 5. Let me just check router 5 here for a second. Well, let's see. This is interesting, but there's an easy way to check this. So the source address is actually coming from the source itself, 4545. But is it really coming from him, or did router 4 just shove that in there? Well, we can check this by checking the source MAC address of this frame to see who it really came from. So the source MAC address came from 8CB6. 8CB6. So did that really come from fast Ethernet 01 and R5? No, it did not, because he is 8E0051. So if we go to router 4, oops, not show run, show interface, fast Ethernet 00.34. There we go. 8CB6. So this is interesting. Look at this. So when the native multicast hit router 4, when he encapsulated that in a register message, hold on a second. I think this is a weirdness of actually, I think I remember this is a weirdness of Wireshark, not actually the sniffer. Yeah, here we go. Okay, not sure why Wireshark does it like this. Up here in the main window, it says it's coming from 4545, but if you actually look in the body of it, here in the IP header, it is coming from router 4. So I'm not sure why the discrepancy here between how it displays it. But so here's my IP header. So it's coming from router 4, going to the rendezvous point, router 3, and then behind the IP header is our PIM header. So type number 1, which is a register packet. And then you can see here there's just a couple of flags, and then here's actually the multicast packet inside of it. Coming from the source, going to the group, and just a couple of things about this in the event that you're curious. I'll talk about null register as the very last thing in this particular video. But this thing here called border, what's that all about? It says no. There's a feature that you can use in PIM sparse mode called a border router or a PIM border router. That is, and honestly I'm not sure how frequently this is used in the real world, but for example, if I had a router that on one side was doing something that's not PIM, for example, it was doing DVMRP, Distance Vector Multicast Routing Protocol, on one interface and doing PIM on the other interface, and we want the multicast to flow through, that would be considered a PIM border router. In that particular case, if that router sent a register, that one bit there, that flag bit, would be set to a 1, saying that yes, he is a border router. But we're not doing that weird kind of thing here, so he's saying no, he's not a border router. So there's our register. Pretty simple, basic PIM header, and then just the actual multicast inside of it. And then according to our whiteboard, we said once that came down, the rendezvous point should then attempt to open up his shortest path tree by sending an S, G join. So let's see here. That is probably this right here, PIM joins. Let's see here. It's coming, the source address is coming from our rendezvous point, 3433, that's router 3. It's going to the PIM address of 224.00.13. Type code 3 for join. Now notice, what makes this different than a star, G join? Well, a couple of things. Number 1, number of joins 1. Remember we saw these flags here of S, W, and R? Well, we don't see that this time. The R meant the RP bit was set, meaning this particular join needed to go up the shared tree. The ultimate destination was the rendezvous point. Well, we don't see that here. The W bit was set, meaning the wildcard bit. The wildcard bit meant that, okay, when you look at this address is the address of the rendezvous point. Well, here, we don't see that. The wildcard bit is not set, meaning that this is actually the address of the source. So it looks sort of like a star, G join, but only until you dig into the guts of it and you see what flags are here or what flags are not here can you actually tell whether it's a star, G or an S, G join. In this case, it's an S, G join. So he says, okay, upstream neighbor, so this is router 4. He says, this is going to you, and I'm trying to join this source and this group. Okay, so there is the S comma G join. And then once that S comma G join is received, that should have put this sub-interface into the outgoing interface list of router 4. And then the native multicast should have come down, and we should have received 2 copies of it, one in a register packet and one in the native multicast itself. So let's see if we saw that. So here is our join. And it looks like, okay, so right here is the native multicast. Notice there's no PIM in here. Source is actually the source. Here's the native multicast. And then right behind that is a PIM register. And here's an interesting question. Are they actually the exact same packet copied? Well, let's see here. In the actual native multicast, in the IP header, we have an identification of 0001. Remember, normally each individual IP packet has a unique identification field. Let's see here. What about the register packet? Has the exact same ID. So yes, these are duplicates of the same packet. All right. And so once we saw that, then we see down here router 3, which is the RP, saying register stop, saying I don't want registers anymore. So right here in the PIM body, type code 2, register stop. And he says I'm stopping for this source and this group. Now there was one other field in the register that I sort of skipped over, a flag that I didn't talk about, which was this right here, the null register flag. What is that? In this particular case, the null register is set to no, it's off. But when would it be on, and why would we use it? So let's say, let's draw something here for a moment, and we can actually use this as an example. Let's say that our receiver was down here, and initially the multicast flow was flowing through the shared tree, through the RP, but we know that within a short amount of time, and we're going to look at this in the next section, we're going to switch over from the shared tree onto the shortest path tree. So let's say that, a few seconds later, all this has stopped, and the traffic is no longer going to the RP. This has been, oops, not that. This interface has been pruned off. Let's just get rid of all this stuff. And now the traffic is flowing in its pure native form this way down the shortest path tree to the receiver. Okay, so the multicast is going, it's going, it's going. It's fine, it's going well. But what happens if 10, 15, 20 minutes later, this happens? We have another receiver who joins our topology, and he wants the exact same stream. So he sends an IGMP membership report. That kicks off a PIM star comma G join. Which creates star comma G state in the RP. And the RP just sits here, waiting and waiting and waiting. Because after all, router Z has no reason to forward this multicast traffic to the RP, right? The RP pruned off this interface. Once the traffic started going down the shortest path tree, we received some prunes up this way. And the RP was told, hey, we don't need you anymore. We don't need the traffic from you. And when the RP heard that, he said, okay, I guess I don't need it anymore. Nobody else wants it from me. So the RP pruned off this link. So that happened a long time ago. Now somebody is asking the RP for this traffic again. But he's not getting it. This is where the null register can come into play. So let's talk about the null register. So we know that after a while the RP may forget about that flow. It went through him originally, he prunes it off because he doesn't need it anymore, and he forgets about it. So what's going to happen here is the router that's connected to the source, router 4 says, well, I've been sending this multicast for a while. There's a chance that maybe the RP needs it. Hey, maybe somebody else wants to receive this traffic. Maybe I should let the RP know that it's still going. Well, we could take the next packet and register it with the RP. That would work. But instead, the designers of PIM said, well, I don't want to keep bothering the RP with this registration because maybe he's got nobody. Maybe nobody that he knows of actually wants this traffic. So instead what happens is every few seconds, router 4 sends what's called a null register to the rendezvous point. What is a null register? It basically looks exactly like a normal register packet, but it doesn't have any multicast data inside of it. So if we go back to our sniffer trace, a null register would say type 1 register, and it would have information in here about the source and the group, but there would be no body. There would be no multicast data inside of it. It'd be a much smaller packet. And the null register flag would be set to a 1. And this is the way that this router here could say, hey, RP, just want you to know, I still know about this flow. It's still going through me. So if you want it, you better tell me. And then once the RP got that null register, he'd say, oh, goody, goody, I've been waiting to hear about that traffic because somebody asked me for it. So now the RP could once again send an S, G join to open up this path, and the traffic could start flowing down this direction. So that's what a null register is. And these are sent every 5 seconds. This is called the probe time. So every 5 seconds, the router that's closest to the source, if the source is still going, if it's still pumping out the multicast, will send out every 5 seconds these null registers to the RP, just reminding the RP that this traffic exists. Because maybe during the last 5 seconds, a new receiver joined to the RP, and maybe the RP wants that traffic again.